Hi, I'm Grant Marshall, and I'll be presenting my experimental demonstration project for Dr. Buckner's MAE ECE 535 Design of Electromechanical Systems class at North Carolina State University. The project objective was to choose an electromechanical principle and demonstrate how its physical application. For this project, I chose to show how a railgun works, which is an application that utilizes two electromechanical principles. The first is Biot-Savart's law, which says that a current with magnitude and direction will generate a magnetic field. The second is Lorenz's force law, which says that a charged particle moving through both a magnetic and electric field will experience a resultant force. So let's take a look at the railgun system and see how these electromechanical principles are applied. The railgun system is composed of 7 components. The first is a power source. For this system, the power is provided by a battery bank consisting of 6 9-volt batteries wired in series, generating a total measured power of 50.1 volts. Second is a set of safety switches, which only allow the current from the battery to flow through the wires when the switches are on. The third is a capacitor bank, which consists of 9 capacitors, each with a 50-volt rating. The capacitors are wired in parallel, resulting in a total capacitance of 17.4 millifarads. The fourth component is a can of compressed air and clear tubing, which will provide the projectile with an initial velocity. The fifth is the projectile and is made out of aluminum. It is bent to a U shape, which will help the projectile maintain its orientation as it slides down the rail channel, as well as allow the projectile to flex in or out on the sides. The sixth component is the aluminum rails, which are 1/8 inch thick, 1/2 inch tall, and 18 inches long. The last component is the rail housing muzzle, which is where the projectile exits after traversing the rail channel. So let's now look at how the electromechanical principles apply to a railgun. If we apply Biot-Savart's law to the basic condition of an infinitely long straight conductor carrying current I, the result is the following equation. H is the magnetic field vector and is related to the magnetic flux density vector by this equation. The theta component of the Biot-Savart law means that the magnetic field follows the right-hand rule and wraps around the current carrying conductor. For the railgun, this means that as current flows through the rail on the right, the magnetic field generated between the rails is upward. As the current flows through the projectile and back down the rail on the left, the resulting magnetic field between the rails is again in the up direction. In the equation for Lorentz force, Q is the magnitude of the charge, E is the electric field vector, V is the particle velocity vector, and B is the magnetic field vector. Applying this to a conductor with finite length gives a force equal to the current times the cross product of the length and magnetic field vectors. Using the right-hand rule, where the index finger points along the direction of current and the middle finger points along the direction of B, you can see that the thumb indicates the direction of the force vector and is pointing towards the muzzle of the railgun. Since the angle between L and B is 90 degrees, the force equation reduces further. It is this force that causes a projectile to accelerate down the rails and out of the muzzle. It can be seen from this equation that to increase the force on the projectile, you would need to increase the current, projectile width, or the magnetic field flux density. So how does this force translate to the projectile leaving the muzzle with a velocity? This is seen by applying Newton's second law to the equation of motion for velocity. In this equation, F over m is the acceleration of the projectile. The previous equation for force can be substituted in to reduce this equation further. An initial velocity is needed so the projectile doesn't weld to the rails due to the heat generated by the resistance of the circuit. The current I and magnetic field B are given by these equations. Substituting these equations into the equation for final velocity, you get this. It can be seen that to increase the muzzle velocity, either current, capacitance, or both can be increased. For a capacitor connected to a battery, the total energy is calculated from this equation. Plugging in the values of 17.4 millifarads and 50 volts, this system has a total energy of approximately 21.8 joules. Now that the basic principles of the railgun are known, the only thing left to do is see it in action.